Understanding the impact of space radiation on cell fate decisions. Exposure to cosmic rays triggers cellular changes, impacting cell fate decisions. Biomarkers can predict cell fate decisions, including proliferation, apoptosis, senescence, and loss of stemness. Biomarkers for space radiation exposure must be sensitive to radiation qualities dose. They should be detectable across various tissue types, easy to measure, quantifiable. High-level radiation can overcome protective barriers in cells, causing complex damage. It leads to the generation of small DNA fragments and inhibits DNA repair enzymes. Ionizing radiation damages DNA directly or indirectly through hydroxyl radicals and reactive oxygen species. High-level radiation produces more complex clusters of DNA lesions. Direct measurements of radiation products have limitations. DNA single-strand breaks and double-strand breaks are more specific markers of radiation damage. High-level radiation can cause DNA damage in non-irradiated cells, inducing mutations and genome instability. High-level radiation has a higher relative biological effectiveness, RBE, and causes more complex DNA damage. It can lead to cell death, senescence, cell cycle arrest. Histone variant H2AX is a marker for DNA damage. The number and persistence of repair foci can indicate genomic instability. DNA repair foci regulate cellular proliferation, replication, and cell cycle progression, replication, proliferation. Unrepaired damaged DNA can lead to senescence or cell death. Persistent repair foci can predict radiation sensitivity and DNA repair deficiencies. High levels of Rad51 repair foci may indicate an increased cancer risk. ROS levels can be measured using redox-sensitive probes. They are associated with various biological outcomes, including cell fate decisions. ROS levels increase following radiation exposure, but the effect depends on the time elapsed and dose. ROS levels are not directly proportional to the dose. ROS may play a role in the bystander effect, but their exact role is still unclear. ROS are potential biomarkers for GCR exposure, but further research is needed to understand their mechanisms. Antioxidants can mitigate the effects of high-level radiation exposure and regulate DNA damage responses and repair. ROS are both indicators and contributors to tissue injury.